Today is the day where we finally connect all of our random items that we've been doing. We've done integrals, we've done rectangles, we've done weird summations. What does any of it have to do with each other? Okay, well, what did we talk about our area in regards to making our rectangles smaller and smaller and smaller? What's true about the area? It gets more accurate, okay? So what we're going to do today is we are going to make our rectangles infinitely small so that we have infinitely many rectangles to get the exact area under the curve. No more approximating. We're going to get the exact area under the curve by taking these rectangles and making infinitely many, infinitely small rectangles. Does that make sense? Okay. This is not the notes I need. Oh, Mrs. Holman, Mrs. Holman. Hold on. Okay, so we are going to take the limit of a sum where we are making infinitely many, infinitely small rectangles. What? Why? Yeah.
I wouldn't dare.
Finish writing this down. I'll be back in 30 seconds.
Wait, we're leaving our English class?
Freaking lie.
Doesn't sound like it.
Okay, so how does this fit in with integrals?
With integrals?
When we find the exact area under the curve, it is actually the integral from where you start to where you stop. This is what we call a definite integral. You have never seen numbers on the integral symbol before, have you? Okay, welcome to the big leagues.
Wait, so we don't have to use that thing?
Oh, we will.
Oh, good.
Today.
Like just hands up.
You know, I'm watching videos, and every time you said something, she would address it.
Well, because he's this right here.
Yeah. My little tiny comments. And
So without a and b, we call it an indefinite integral. With a and b, we call it a definite integral. And what we are finding when we take an integral from A to B, I never changed your attendance. So when we take the integral from A to B, we are finding the area under the curve. So curve back to the x-axis. Okay? So how does that fit into our infinitely many, infinitely small rectangles? Okay? We'll get there. I'm going to come back to these at the end. Okay? I'm going to come back to these at the end. We're going to go through a couple summations so you can kind of see some patterns and use them in your work this evening. Okay? What happens? Okay, write it down first. There's a lot to write down. Sorry. Shortcut. What's the sum from 1 to n of 1? N times 1. So we have the limit as n approaches infinity of 1 over n times this is n. What's our limit?
1.
Okay. Next one. Okay. So now that we have the limit of 1 over n squared times, what's this shortcut? Okay. Let's go back to our rules on limits. Our numerator has n squared, our denominator has n squared, and we have a limit towards infinity. That means we can look at the horizontal asymptote. Is that correct?
Yeah.
Okay, so I have n squared plus 2n over 2n squared. So our limit is 1/2 because we look at the coefficients of n squared in this case. We have n squared over 2n squared. So our horizontal asymptote would be 1/2. Do you think you know what's next? Really, I'm going through these so you can remember how to evaluate limits towards infinity. And these are the groupings you'll see in your Riemann sums that we go through here in a moment. Okay, so we have the limit as n approaches infinity of 1 over n cubed times this shortcut. This is a long one, right? Ugh. Okay, so let's talk about what we have. We have a cubic over a cubic, yeah? And when our degrees are the same, we can look at the coefficient. So what's the coefficient for n cubed if we were to multiply this out? This is 2n cubed. And down here we have 6n cubed. Okay. Speculating. Our next limit, what is it going to equal?
1 point.
Gosh, I hope so, right? Last one. This is why I had you remember the shortcuts and not make you use them in your, or not make you do summations in your calculator. Because in Riemann sums, we have to do everything in terms of n. You have to know the shortcuts. Your calculator's not going to help you. Okay? So in this case, we have the limit as n approaches infinity of 1 over n to the 4th. And then the sum of k cubed becomes n times n plus 1 over 2 squared. Well, do you agree that we have a 4th degree over a 4th degree? Once again, we have the same degree, numerator and denominator, so we can look at the coefficients for our limit towards infinity. What would the coefficient of n to the 4th be in the numerator? What would it be in the denominator? 2 squared, which is 4. Okay. So in our Riemann sum problems, you will always have the case where you have your degrees that match up like that. Okay? Where you can look at the horizontal asymptote by looking at the coefficients of the leading term. Okay? Now, what I want you to do is just put your pencil down. I'm going to talk through some things. Okay? Okay. So we have a function f, and I've given you an interval from a to b. Okay? Just like I did for your quiz, I don't even know, Tuesday, right? Okay, I gave you a function, I gave you an interval, you found me the area, right? Okay, what we're going to do is we are going to break up, so when you see the word partition, that means like break apart, okay? We're going to partition this into infinitely many rectangles, so we're a lot of these rectangles between A and B, okay? And for now, we're actually going to have a number, we're going to have n rectangles, okay? We have n rectangles. Okay. Yep. Gonna get that symbol fixed. Okay, so our width of each subinterval is delta x. Okay. And C is just any point on the interval. Okay, I know that there's a lot of notation happening here, but I'm trying to talk simple for you, okay? We have n rectangles, and they have width delta x. That's really what we need to be concerned with, okay? So what we're going to do is we're going to add up our rectangles. So let's think about when we did this as a class, well, over the past week. We would take the thickness, delta x, of our rectangles times the height, which we got by plugging in x for a function value, right? Delta x times function value, delta x times function value. Well, now what we're going to do is we're going to put that shortcut in our summation, okay? And in order for us to get the exact area, then we're going to actually have to take the limit towards infinity. So instead of having n rectangles, we want infinite rectangles. And once we do that, instead of giving an over or an under approximation, we're going to get the exact area. Because all of those rectangles are infinitely thin to where it's like you're just drawing a line to color it in. Does that make sense? Okay. So, we're going to come back to this. We've seen this slide before, right? Okay. Now, what we are going to do to make our Riemann sums easier, that's what this is right here, is we are going to use a right-hand approximation. Okay? So, in order to use this right-hand approximation, we are going to need to establish what x sub k is. Okay? Where are we going to start? So, let me ask you this. If I gave you an interval from 1 to 3, and we were doing right-hand rectangles, would f of 1 ever be in your work? No. Where do we begin? Okay, f of 1 plus delta x. Okay, so that's that same thing here. The first time we throw something into f, it's wherever the interval starts plus delta x. Okay, so that's what we're going to need to consider. When we set up these Riemann sums. Well, because we might not start at like 0, so k would be wherever we begin. Okay. Well, a would be where we begin, but k is what we start plugging into. Okay. So we begin our interval at a, and then we add delta x to get our next rectangle. And then we add 2 delta x to get our second rectangle. And then we add 3 delta x to get our next rectangle. That's why this k is here. We start at our interval, and then we add delta x however many times to get our next rectangle. Okay. And since we're taking the limit towards infinity, these rectangles become infinitely many, infinitely small, and we get the exact area. Are you ready? Okay. I will warn you that this will probably be the most amount of work we'll have to do on a problem in this chapter.
I was hoping you could just the last time.
Yeah.
What was that for? It was orange. We was like keep on rewriting.
Okay, so on your paper, I would write down y equals x squared, and then from the interval, it looks like this graph is going from 0 to 5. That's what I would write down on your paper. You don't necessarily have to draw the graph if you don't want to, but that red shading, that's what we're going to find. Okay? And what I need you to understand is that the area under the curve x squared from 0 to 5 is represented by the integral from 0 to 5 of x squared dx. That is what we are finding. Okay, so when we did our rectangles, the first thing we determined was what? Okay, usually they gave us n, right? And then with n, we could find delta x. N just gets to stay n in these Riemann sum problems, but we can figure out with n what our delta x is. So delta x we calculate by taking b minus a over n. In this case, b is 5 minus a is 0 over n. So delta x is 5 over n. Okay. That's important. Okay. Then I want to think about what that x sub k would be. Since we're using right-hand Riemann sums, we need to take a plus k times delta x. Not sure why I made such a small delta there. So we know what to plug into our function. Okay. Well, what's a? A is 0 plus k times delta x. So essentially, we have 5 over n times k. It's nice in this example that a is 0, which is why I started with this. Okay. Deep breath. So the integral from 0 to 5 of x squared dx. I'll keep going back there.
Because you said deep breath.
I know, that was like for me and for you. Like, hang with me here. So our definite, thank you, integral is the limit from, as n approaches infinity, of the sum k equals 1 to n of what goes inside of our summation. Okay, so we need the f of x of k, right? Okay, so don't write this down yet. This is what goes in our summation. So our function evaluated at x sub k, well, let's do this. We know that x sub k is 5 over nk, right? So I'm going to write that first so we can see where everything's coming from. So what happens is we have the sum from k equals 1 to n. Our function is x squared, so we get 5 over nk squared, and then delta x is 5 over n. Our function is y equals x squared. So f of this means, hey, plug this into our function, which is x squared. So x squared. Yes? Okay. So now what we have is the sum from k equals 1 to n of 125 over n cubed times k squared. Do you agree? This is 5 squared, which is 25, times 5 is 125. This is n squared times n is n cubed, and then the k is squared. Okay. Well, what did I tell you you can do with constants? Can we take constants and throw them outside of our summation? Okay. So as n approaches infinity, I can take 125 over n cubed, and I can throw it outside of our summation, so that now we have the summation from 1 to n of k squared, and we have a shortcut for that, don't we? Okay. Our shortcut for the sum of k squared is n times n plus 1 times 2n plus 1 all over 6. All right, do you see where this is going? We no longer have a summation. We only have a limit. Now, this right here, this is what we talked about on the slide a few previous, right? Towards infinity, if I have 2n cubed, blah, 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 over 6n cubed, what's our limit? 1/3. So we have 125 times 1/3. We have exact area. We evaluated the limit towards infinity by looking at all the ends, right? Like we did on that slide previous. We had a cubic over a cubic, right? So we know we can look at the horizontal asymptotes. So the coefficient of n cubed here was 2. The coefficient of n cubed here is 6. So 2 over 6 gave us that 1/3. Okay? You're right. If you make a mistake, it is going to affect the rest of the problem, which is why you should do this very carefully. Like, this is not a problem you rush through. Okay? I will be very honest with you. You will have one of these on your next quiz, and you will have one of these on your test. But by the time we get to the quiz and the test, you will know what the answer is before you even do the problem. Okay? More than, let's take like the trapezoid problem on the quiz yesterday. This would be worth a couple more points than that. Because, are you doing a little bit more work? Yes.
It's unfortunate.
No. Let's go back and look at that. Hold on. Because K was only here. Okay. The N will always be one more than K. All right. So if you're not drawing the graph and just writing an interval, what would our interval be? -2 to 2. That's like burnt red. Is that burnt red? -2 to 2 is where our shading is. Okay. So what we are looking for is the integral from -2 to 2 of our function 4 minus x squared. And we're doing so with respect to x. What's different about this problem? Our a is not 0, that's going to make a big difference. Our function also has more than one term, that's going to make a big difference. Okay? Is it something we can't handle? Of course not. All right. First thing we need to calculate is delta x. B minus a over n would be 4 over n. X sub k. A plus I'm going to write it as 4 over n times k, since k is like the first variable we have to take care of. Is that okay? Okay. You ready? No?
Yes.
So the integral from -2 to 2 of 4 minus x squared dx, we calculate that value exactly by taking the limit as n approaches infinity of our rectangles. K equals 1 to n. And I'm gonna write really simply. first, just so we remember where everything's coming from. Okay? So we have our rectangles that we're adding up, and this limit that we put out here makes those rectangles infinitely thin and infinitely many, and that's how we're getting the exact area. Okay? So now, f of x sub k. We know that this is x sub k right here, and we know that our function is 4 minus x squared. So when we're looking at f of x sub k, we're talking about plugging x sub k in for our function. Well, our function is 4 minus x squared. And then we have to multiply our function by delta x. What's the problem? So this is 4 minus x squared times delta x.
I forgot the 4 minus.
Okay, so now we need to do some calculating and like simplifying in here before we can break this up into our rules. So the first thing we need to take care of is this right here. We can square binomials without having to put all of our work down. Okay? A times A would be, okay, 4. We would have A times B twice. We have negative 2 times 4 over nk, which would be negative 8 over nk, and we have that twice. If you need to put out FOIL and do all 4 terms, you go for it.
That's on my quiz.
And then we have this guy
You know it's in like the top and then a raise.
squared.
Yep.
Click on season. Scroll down.
Okay, are you okay with that?
Any better.
Well, a little bit, because what's going to happen here?
Out of there.
Yeah. So now we need to take care of that subtraction, which actually helps us, because 4 minus 4 is
0.
yes, and we end up with a positive 16 over nk minus 16 over n squared k squared. All of that still times 4 over n. McKenna, does that help? Like the 2 times negative 2 is the 4. And then the negative 2 times this, and negative 2 times this got me here. And then this guy times this guy. Okay, was that needed? Okay. All right. We're getting closer, right? Okay. Now, we need to multiply that delta x through. Now we have 64 over n squared k minus 64 over n cubed k cubed. And now we finally have something we can work with. Once you get to the point where you have individual terms, we can break this apart into, since we have two terms, can we break this apart into two summations like you did on your quiz Tuesday? Okay, you had to do that on both of them, didn't you? The two problems I gave you on your quiz? I don't know. That's a 2.
Okay.
Sorry.
That is just us following the line.
Hang in there with me, please. So since we're summing up K, I'm going to take 64 over n squared and throw it outside. And then 64 over n cubed and throw that outside the next one. And now we can use our shortcuts. Woo! The sum of K. To be honest, this was like not the lesson I wanted to have after a snow day. You don't come back in the best moods after a snow day because you really enjoyed your day at
I
home,
was ready to rock and roll.
right? Were you? Good. And then our shortcut for K squared. Oh, there we go. Okay, so you can do one of two things. You can remember those limit shortcuts, or you can combine everything into one step. If we were to multiply everything right here, we'd have 64n squared, blah, 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 over 2n squared. So towards infinity, our limit would be 64 over 2. Over here, if we multiplied everything out, we would have 128 n cubed, blah, 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 over 6n cubed. Yep. If we multiplied everything out here, we'd have 128 n cubed, blah, 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 over, you know, this would be 64, sorry. I thought I was excited about the 30. So we have 128 cubed, blah, 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 over 6n cubed. And so then our horizontal asymptote would be 128 divided by 6, which is 64 thirds. So then when you take 32 minus 64 thirds, you get 32 thirds. Woo! You know how I was looking for my notes? Now I go print them off. Got it.
We don't have time for this.
I know. In addition to your homework. So I want you to skim through page 270. And from those pages, examples 3 and 4 are important. And theorems 4.6 and 4.7 are important. And that is what I'm looking for. Okay. I then have one thing for you to write down in your notes that will aid in this. Okay? None of you are going to do anything but just put your notebook away right now.
Sounds about right.
So you can take 1 minute.
What are we doing?
It's 11:33, people.
Oh, I thought you meant tomorrow. Okay.
No.
Right.
Still taking notes?
I told you what was going to happen. You know what? You're going to write these down in your notes. Just kidding. You're going to write these down when you read through these pages. Okay, you're going to write those down when you read those pages.
Work today, team?
I would do the assignment, and then after the assignment, look at those pages. Okay? This will be where we start notes tomorrow. I promise you that what you're going to look at in the book right here is going to be way easier than what we did today. Do you believe me?
Yes.
Okay. Like, we're talking, like, wait. Yeah.
And trios.
That is because since they're independent, you're going to have to find each property
Just understood that because remember how I was working out and I was already and then I got 100 points. I was like, I'm so yeah. Yep. I have not started.
Oh, it's because you use your delta x right here. Like you need to find f of negative pi over 2, but then you add delta x for your next one. So then f of negative pi over 4, and your next one is 0, and pi over 4. Like you did up here, did you do it up there?
Yeah.
You did not do that here. You just did it. You didn't do anything.
What?
That's fine. Yeah. Make sure you at least read those so you know what we're doing in class tomorrow, okay?
Thank you.
I don't know if I should try to work. Well, I'm gonna ask